Hello everyone. In this video, I'm going to solve three problems related impulse and momentum and one problems related to conservation of energy. The first problems. Prior to the context, the disk A has a counterclockwise angular velocity and the disk B is stationary. It's meaning omega for and disk B is 0. As a result of friction, the angular velocity of disk A decreases and clockwise angular velocity of B increases until there is no escape between the disks. What are the final angular velocity of these two disks and the moment of inertia of the disk are I sub A and I sub B. We have informations. All the nouns for this problem is a radius RA and RB. I sub A, I sub B, and initial angular velocity for disk A. Based on this information, we are trying to solve the problems and find the omega A and omega B. For solving this problem, first we are drawing a free body diagrams. Based on the information of the problems, this is the disk A, and this is the initial angular velocity. We have a pin here. This is the AX, AY. Also, we have weight of this disk. This is before the contact and after the contact, the disk B and the disk A has an angular velocity of omega. And this is the weight of this. Once the disk A is rotated in this way, the friction is opposite of the motions. For this reason, the frictions is applied in this way because the friction try to reduce the speed of the disk A. This is all the information for disk A, and this is disk B. At the start point, the omega is 0. This is Bx, By, because we have a pin here. This is before the contact. But after the contact between the disk A and B, the problem showed that the disk B start rotating clockwise. This is about direction of the omega. Now we are drawing a free body diagram for disk B again. This is the friction force, okay, and these two disks has a contact together without any vibrations and without slip, okay, for this reason. Based on third law, Newton's third law, we have action, reaction with the same magnitude but in the opposite direction. This is the F for disk B. Also, By, and this is the weight of the disk B. This is the free body diagram for these problems, and now we are applying the angular impulse and momentum for both of these disk, because as you can see, mm, these two disks just has a rotations. For this reason, just we are using the angular impulse and momentum. Disk A, um, we are using this equation m dt h2 minus h1. We are finding the angular impulse at the center of the points of each of the disks. If we look at the free body diagram for the disk A, as you can see, the only force that make a rotation or make a movement at the center of the disk A is a friction force. But these two pin reactions and the mg or the weight of the disk is passed through to the center of the disk and doesn't make any momentum or moments. For this reason, for moment part, just we are involving with one force, and this is the friction force times the radius of the disk A, and the rotation is a clockwise. I previously mentioned when we are using or when we are applying the principle of impulse and momentum, and equation of motion is Newton's second law for the rigid body. And we are always keep the sign of the moments, which one as a clockwise and which one as a counterclockwise. This is as a clockwise rotations. For this reason, we have negative F R dt. This is from time 0 to final times. How about the H? H is an angular momentum and is found based on the moment of inertia times omega. For the disk A, the figure is shown after the contact. The disk A is keep rotating the counterclockwise. For this reason, the sign of omega is positive. We have IA omega A, and this value is unknown, and we have to find it. Minus I, the moment of inertia for disk A times initial angular velocity. Based on the information of the problems, the initial angular velocity of the disk A is a counterclockwise. For this reason, the omega, the sign of the omega is positive. This is about the equation 1 for disk A. This is the final times. This means at this time we are trying to find the omega A. For disk B, exactly we are applying the principle of angular impulse and momentum from time 0 to the final times. Okay, this is as an unknown. Sorry, this is nouns. Okay, just the omega A and omega B as an unknown. Okay, look at the free body diagram for the disk B. As you can see, the pin supports and the weight of the disk B is passed through to the point G or the center of the disk B. For this reason, these three components doesn't make any moment or make rotation. The only force that make a rotation for this problem is a friction force. And what is the moment? Is R, the radius of the disk B. This is the RB times frictions. And as you can see, it has a clockwise rotation. For this reason, once we are applying the angular impulse and momentum for disk B, this is the friction force This is the radius of the disk B. And how about the sign? Is a clockwise. It's negative dt. Because this part is talking about the moment, that's meaning this part. And now we have to take an integral respect to the time. How about the right side? Now we have moment of inertia for disk B, omega B. But look at the problems. Once we look at the problem mentioned after the contact, the disk B has a clockwise rotations. For this reason, the sign of omega B is a negative. Minus the initial angular velocity for disk B is 0. For this reason, the h sub 1 becomes 0. This is the equation 2. If we are divided the equation 1 and equation 2, as you can see, we can remove the friction force because we don't have any information about the value of the friction force, and both of these two components has the same value. Because as I mentioned, based on the third Newton law, we have action, reaction has the same magnitude, but in the opposite direction. By equation 2, okay, force times R is show the moments. Now for the top, we have IA omega A minus IA initial angular velocity for disk A. For disk B, just we have I sub B times omega B. And this negative is related to the clockwise rotation of this disk B. Once we divide these two equations, the friction and dt will be cancelled out, and we have RA over RB, negative is cancelled. Now we have IA omega A, A. This is the equation that we are finding based on the dividing the equation by equation 2. As you can see, now we have one equations with two unknowns. The omega A and omega B has an unknowns value. We need to know, we need one more equations that the problem become as a determined equation. Based on the information of the problems, after the contact, the disk A and disk B, after the contact and settle, okay, there is no vibration and slip between these two disks. Based on the rules that we learned in the chapter 17, we can say the velocity of the disk A equal the velocity of the disk B, also tangential acceleration for disk A equal tangential acceleration for disk B, also about the displacement. This is the three rules that we have to know that when we have this type of the motions. For this problem, just we are using these informations, okay, because we are looking for omega. And once we write the velocity at A equal the velocity at B. If we are trying to write based on the R and omega, we have RA omega A, RB omega B. Okay, now this is equation 3. Mm, This is equation 4. And now we can solve the equation 3 and equation 4 and find the value of the omega A and omega B because we have two equations with two unknowns. Omega A, omega B, omega A, omega. Once we solve these two equations, the value of the omega A will be 1 over. This is about the angular velocity of the disk A. This is for disk B. This is the answer of this problem. As you can see, this problem has a parametric problems. But the important part, okay, is how we are writing these equations, okay? It's meaning equation 1, equation 2, and once we don't have more information, and we know that the time and the friction force has the same value for both of the problems, we are divided and we find the equation 3. And at the contact points between these two disks, we are using these equations. The velocity at A equal the velocity at D. Next problem. These problems, okay, show the flywheels that is attached to the electric motor and that the initial velocity is 0. And once the system is mentioned initially at rest, is meaning velocity equals 0. Also, the angular velocity is 0. The motor exerts a couple by this equation on flywheel, and the moment of inertia for the flywheel is given. For part A, we should find the angular velocity of the flywheel at time 10 seconds, and also for part B, we should find the maximum angular velocity angular velocity will the flywheel attain. For these problems, we have information about the initial velocity. Initial velocity of the motor. The problem is mentioned at the rate. Once the velocity is 0, because the flywheel is attached to the motor, they have a same angle, same velocity. For this reason, the velocity of the flywheel also 0. And we know that the omega also is 0 because velocity equal r times omega. Once the velocity is 0, omega will be 0. This is about the initial velocity of the systems. Also, the moment of inertia for the flywheel is given as a 10 kilogram times meter square. This is the moment of inertia. Sorry, this is the moment is given as these functions. We should find the velocity at time 10 seconds. What is the value of the omega? For these problems, again, flywheel just has a pure rotations. Okay, for this reason, we are applying the angular impulse and momentum. This is the equation. M dt equal I omega to I omega, or h sub 2 minus h sub 1. Based on the information of the problems, the initial angular velocity is 0, and just this force is up, and this moment is applied to the flywheel. Now we have 200 and from time 0 to time 10 seconds, because we have to find the omega at time 10 seconds. The moment of inertia is given as a 10 kilogram meter square omega 2. Once we take an integral from these equations, we have 200 e over these coefficients from time 0 to 10 seconds, 10 omega 2. Once we plug the upper and the lower limit in these problems, the value of the omega 2 become, this is 10. The answer of this integral is 1264.24, approximately at the 126 radian per second. The angular velocity of the flywheel at time 10 seconds is approximately 126 radian per second. For part B, we should find the maximum angular velocity. Once we look at the angular impulse functions, okay, it shows that the functions, okay, or the angular velocity of the flywheel is increasing because this function has a monotone functions of the times, okay. For this reason, the greatest or maximum value occurs when the t for these functions approach to the infinity. So for finding the maximum angular velocity, the time should approach to the infinity again, because this is as a monotone function, and by increasing the times, okay, the value of the omega will increase. Now we can say the maximum omega is a 210. This is as a moment of inertia. Let's maybe write this one. 1, okay. The infinity, the upper limit of the integrals is infinity and the lower is a 0. Now we have 1 minus b 2. Okay, and the answer is 200 radian. Once the time approach to the infinity, we can find the maximum value of the angular velocity, and it's a 200 radian per second. Okay, next problems. These two gears is given. The information of these two gears is given. The mass of A is a 10 kilogram. The moment of inertia for this A is 0.064. And this is the moment of inertia for gear B. And based on the problems, these external moments is applied on a gear A. And we should find the angular velocity of the gear B after 5 seconds if the gears start turning from rest. Point 1, 2. This is all the information that we have for these problems. And based on these problems, we have this force and this external moment that apply on a gear A, and this is for gear B. And we have to find the omega at time 5 seconds. Also, the problem mentioned at time 0, the disc A and B, the gear A and B are stationary. For this reason, the velocity of the gear A is 0. For gear B is 0. Also, we can say omega A at the initial time or at time 0 is 0. This is for gear B. The first step for solving these type of the problems, okay, draw a free body diagrams, because the equations for solving this type of the problem is the angular impulse and momentum is mdt I, or for example h2 minus h1. Okay, and as you can see, we have to find the moment. Okay, for finding the moment correctly, if we have some force, we should draw a free body diagram correctly. First, I draw the free body diagram for this A. Okay, this is the radius of the gear A. This is the weight of this gear. There is a pin. We have A, AY. Okay, these are the reactions. And the problem mentions this external moment apply on a gear A. Okay. And once the gear A is rotated the clockwise, the friction force is applied against the motions. For this reason, this is the friction force for the gear A. This is all the information that we have. And about the kinetic diagram, we can say the gear A, the rotations in this way. The next one is about the gear B. For gear B, there is no any external couple moments or external moments, okay? For this reason, just the reaction of this force is applied on a gear B, okay? This is the direction of the friction for gear A, and reaction is applied for gear B. This is the weight. This is the pin reactions. And how about the direction of rotation for gear B? Okay, this is gear B. Once this friction force is applied on a systems, okay, on a gear B, the gear B start rotating counterclockwise, okay? For this reason, the omega B direction is counterclockwise. Based on this free body diagram and this equation, we are trying to find the value of the omega for gear B at time 5 seconds. First, we apply this equation for gear A. Okay, for the gear A, we have these external moments and the directions is clockwise 10, and this is as a constant value. For this reason, we can write the mt instead of the integrals, m delta t, sorry. Okay, now we have these moments times t. The t for this problem is 5 seconds because we should find the omega at time 5 seconds. And another force that make a moment for the gear A, okay, the friction force. And how about the directions? This one is make a counterclockwise rotations for the gear A, okay. For this reason, we have the friction force times radius of the gear A. Okay, this is talking about the moment, the first part of the equations times dt. Okay, again, for these problems, okay, we are working with the constant value. Instead of integrals, we can write the m delta t times delta t. For this problem, the delta t as a 5 seconds equal the moment of inertia for gear A is 0.064, okay, because h is talking about I times omega. This is the I, and the angular velocity for gear A after the contact, okay, is clockwise. For this reason, we have the negative omega This is all the information for the gear A. Now we are applying the angular impulse and momentum for the gear B. Okay, for the gear B, once we look at the free body diagram for this gear, the only force that make a movement or rotations, okay, for this friction force, okay, and once is applied, the gear B start rotating the counterclockwise, okay, for gear B, we have friction force times radius of the gear B. Okay, this is become as a moment times delta T for these problems equal the moment of inertia for disk B times omega B. How about the direction of the omega B is a counterclockwise. For this reason, the omega B is positive. But how about the disk A is clockwise? For this reason as a negative. If you look at these two equations, as you can see, we have two equations with three unknowns: frictions, omega A, and omega B. Again, we need one more equations to make a problem as a determining condition. We know that when the gear A and the gear B mesh together without any slipping, okay, and vibrations, at the contact point, the gear A and the gear B has the same velocity, and we can use these equations and write the third equation. We have the velocity of the gear A and the velocity of the gear B at the contact points between these two gears has the same velocity, RA, omega A, RB, omega B. This is equation 3. Now we rewrite these three equations, okay, based on the nouns that we have, okay, because we know that what is the radius of the gear A, gear B, okay, and also about the moment of inertia for each of these here. For gear A, okay, we have -10. This is the external moment again, okay, times delta T. For these problems at 5 seconds. The friction force times the radius of the gear A. The radius of the gear A on a figure it shows a 0.1 meter times delta T, again 5 seconds, equal -0.064 omega. This negative because the rotation of the gear A is a clockwise. For gear B, we have friction force, radius of the gear B times T or delta T equal the moment of inertia 1.125 omega B. We have 0.1. This is equation 2, and equation 3 we have 0.1 omega A, 0.2 omega B. For this problem, we have to find the value of the omega B. For this reason, we can write the omega A based on the omega B, and is a 0.2 over 0.1 omega B. It's meaning we can say the angular velocity of the gear A is a 2 times of the gear B. Okay. Now we rewrite the equation 1 based on this. Omega A is a 2 times of omega. If you look at these two equations, now we have two equations with two unknowns, friction and omega B. Once we solve these two equations, the value of the omega B at time 5 seconds, it will be 72.4 radian per second. This is the answer of these problems. And the last problems is about the conservation of energy. We have informations about this system. Based on this figure, once the spring and the rod, okay, has an angle as a 0 theta, the total length as a 2 meters, we should find the angular velocity of the rod when the theta as a 30 degree. The one thing I want to correct here, once the theta equal 0, sorry. Once the theta is 0, the spring has honest stretch. Okay, stretch conditions. Okay, based on these information, okay, we are trying to find the value of the omega when or angular velocity of the rod when the theta at the 30 degree. Let me draw a free body diagram. This is 2 meter. This is the rod. The total length of the rod is 1.5 meter. And this is the spring that is attached. Okay, and the problem mentioned at theta 0, once the theta is 0, okay, the spring has the on a stretch conditions. It's meaning the length of the spring will be 0.5 because the whole length as a 2 meter. Once the theta equals 0, the on-stretch length of the spring, I show S of U, is 0.5 meters. Also, the problem mentioned at theta 0, and the velocity or the system release from the rest. Okay, once the velocity is 0, also we can say the omega for this system will be 0. For these problems, we should find the omega once the theta is 30 degrees. Okay, the first step, we should draw a free body diagrams once the theta as a 30 degree. The whole length is 2 meters. Okay, once the rod is make a 30-degree angles. Okay, the spring will be stretched. This is the spring. Okay, this is the length of the rod. Okay, the length of the rod is a 1.5 meter, and as you can see, the rod when it's rotated, okay, has a rotation plus translation. Okay, for some for at least for most of the points, or I can say for all the points except the points that is connected here. Okay, this point just has a rotation, but other points entire of the rods has a translation plus rotation. Now we are applying the conservation of the energy at the center of the mass of the gear and this system or the rod. Okay, this is about the G, and the G is located at the middle of this rod. Okay, this is the information that we have. Okay, this is mg. Now the next step for applying the conservation energy, if you remember, we should set up a date. I set up a datum once the theta as a 0 degree. At the datum, the T1 or kinetic energy is 0 because the problem mentions the system released from rest. And the spring and the condition of the spring as an unstretched. For this reason, the elastic potential energy will be 0, and also we set up as a datum. For this reason, the gravitational potential energy for this system is 0. It means the total V for this problem is 0. This is about once the theta as a 0. But once the angles is 30 degree, now we have to check, we have to find the potential energy and kinetic energy. For potential energy, once the theta is 30 degree, as you can see, for the problems or for this system, we have a spring plus the elevations. Okay, for gravitational potential energy, because it's happened below a datum, we have a negative potential energy. We have negative, the mass of the rods is 30 kilogram, mg, see the gravitational potential energy, mg times h. This is below a datum, we have negative 30 g. And how about the height? We are working with the rigid body, okay? And if you remember, I mentioned we are applying the kinetic energy and potential energy at the center of the mass of the object, okay? Or if you want to apply for another point, you should know that what is the moment of inertia is mean the odd for other points. Okay, for these problems, we apply at the center of the mass of the rods. Okay, for this reason, the elevations is 1.5. This means the perpendicular distance. Okay, this is 30. Is at 1.5 sine 30. But look at the problems. This is about the rigid body. Okay, for this reason, if you are trying to find the gravitational potential energy at the center of the mass, okay, just we are working with the half of this length, okay. This is the about the whole length of the rods, okay, is a 1.5 sine 30, but we are finding the gravitational potential energy at the center of the rod. Okay, for this reason, we should consider the half of the length of the rod equal. This is about the gravitational potential energy, and the value is 100. 110.4 Newton meter. This is negative because it's we set up theta as a 0 as a datum point. The next one is elastic potential energy. The elastic potential energy, we know that always positive, half of the kx squared. The value of the k or constant of the spring is given as a 80 Newton meter, okay, per meter. Now we have to find x. At the in the problem mentions once the theta as a 0, the spring as an unstretched condition. Okay. Now we have to find the length of the spring at this condition. Okay. The length of the spring at the once the theta as a 30 degree is fine based on this equation. Let me draw it. Okay, we have to find this length. This is the rod. Okay, this is the rod. This is 30. Okay, for finding this length, we need to know that what is this height. Okay, this is 1.5 sine 30. How about this length? For finding this length, we know that the whole length of the systems is 2 meters. How about here? Is a 1.5 next to the angle cosine theta. For this reason, this area I show by A, okay, is a 2 meter minus 1.5 cosine 30. Okay, now we have informations about these two sides. Okay, 2 minus 1.5 cosine 30. And we can find the length of the spring. This is the 1/2 K. We have 1.5 sine 30 squared plus This length, we learned that this is as a 2 minus 1.5 cosine 30. Okay. This is the length of the spring at theta equal 30 degrees. But the problem gives us the information about the unstretched length of the spring. For this reason, we should subtract from this value. This is 0.5. Now the whole of this answer is parentheses to the power 2 because we know that for elastic potential as a general plus half of the K S minus, if we have information about the unstretched length of the spring, we should subtract from S. And once we find this, once we calculate here, the elastic potential energy will be 6.444 Newton meter. This is about the elastic potential energy and gravitational potential. The next one, we should find the kinetic energy. For kinetic energy, as a general, we have two parts, okay? Let me write the whole of the equation. T1, V1, T2, V2, okay? These two parts is 0. Now we have to find T2 and V2. For kinetic energy for the rigid body, we have two equations. Okay, the kinetic energy has a two parts. Half of the mv squared, this is about translations, and this is about the rotations. And the summation of these two components is show the kinetic energy at position 2. But we are working with the rigid body. We should know that we are applying the kinetic energy at which points. We are applying at the center of this rod, okay, because we find the gravitational potential energy at the center of the mass of center of the gravity of the G or rod. For this reason, these two components should be right based on the center of the rod. We should modify. But how about the omega? The omega for entire of the rod has the same value. The mass of the rod is 30. How about the velocity? Is a velocity at center of the mass of the rod. The moment of inertia for the rods is found based on these equations. During the time of exam and quizzes, I will give you the equations or the exact value of the moment of inertia. This is the equation for finding the moment of inertia for rod. We have 112. The mass of the bar is 30. The total length is a 1.5. Okay. This is moment of inertia for the rod. Okay. Omega square. This is the two parts or two components of the kinetic energy that we have to add. But if we back to the problems, once the theta is a 30 degree, we should find the omega. For this reason, it's better to write, okay, the velocity based on the omega. Because if we are keeping the velocity as a velocity, okay, then we will have one equation with two unknowns, velocity and omega. For this reason, we will rewrite the velocity at the G based on the omega. The velocity at the center of this rod equal the R times omega. What is the R? The R is meaning the length of the rod from this point to the center. Okay? It's meaning we are working with the half of the length of the rod. Omega. Okay? Now, based on this information, we write the conservation of energy. T1, V1, T2, V2. At the initial condition, kinetic energy and potential energy is 0. Once the theta is 30 degrees, the potential energy has a 2 components. This is about gravitational and is a negative because below a datums. And this is about the elastic. For kinetic energy, we have 2 components. Okay, this is about rotations. Okay. This is the whole of the potentials. Okay, and half of the m velocity at the center of the gravity that we are substitute by r times omega, but just we are working with the half of the length of the rods because all of these equation is applied at the center of the mass of the rod. Okay, this is the R times omega squared. Okay, half of the mv squared. Now we write based on omega or omega plus these parts or this component of kinetic energy plus half of the I omega squared. Okay. Now we have one equations with one unknowns. These 2 components about the potential energy. This is about kinetic energy. Once we solve these equations, the value of the omega will be 3.404 radian per second. This is the answer of these problems. Just as a quick review, the potential energy, once the system has a general plane motion, has a 2 component, half of the mv squared plus the half of I omega squared. What is the I? Is the moment of inertia. Okay, and at different point has a different value. For this reason, it's very important to know that we are applying the conservation energy or principle of work and energy at which points. Okay, for example, if we are writing this, if we are writing the kinetic energy at the center of the gravity or the center of the mass of the objects, we have to mention this is the velocity at the center of the mass of the objects, and this is the moment of inertia for the center of the mass of the object. Okay, for this problem, the moment of inertia of the rod at the center of the mass is found based on this equation. What is the L? Is the total length of the rods. Okay, for this reason, if you look at the equations, I'm working with the whole length of the rods. But how about the velocity? Velocity at the center of the gravity. For velocity at the center of the gravity is mean at these points, okay, we are working with the half of the length of the rods. If we are writing based on the r times omega, we have half of the length of the rod times omega. This means 1.5 over 2 omega 0.75. Okay, see, I'm using this term for the linear translation motion for the rods. This is all the information that we have to know that for these problems. Okay, the gravitational potential should apply at the center of the rod, and for elastic potential energy, we have information about the unstretched length of the spring. For this reason, we should subtract from the length of the spring at once the spring or once the system, the angle is 30 degrees. And this is S sub U is meaning unstretched length of. This is about the answer of these problems, and thanks for watching.